Welcome, Professor Fässler. We are happy to have you here today. And congratulations for receiving the Arfvedson Schlenk Award. You have been honored for outstanding contributions in the field of lithium chemistry. Can you say a bit about your research in this field?
Yes, first of all, thank you very much. I think we all faced once the problem that we wanted to use a mobile phone and then the battery was empty. And in a more general sense, this means that we have a demand for more energy storage possibilities. And in a simple way, a battery is composed of anode material, cathode material, and an electrolyte in between. And this is where the element lithium comes into the game. Lithium is a light metal. It's not heavy, so it's good for mobile application. And it has a high reactivity, which expresses that it has the possibility to store lots of energy, which gets free when it starts a chemical reaction. And for this, lithium-ion batteries, these are the most common batteries to store energies. And this is getting a further demand. If we have renewable energies, we want to store energy because it's not always produced at the time when we need it. And for lithium is, so one demand is to make batteries with higher capacity, so we can use like a mobile phone longer, but it also, we need a better safety for the batteries. So we sometimes read reports that laptops are burning or e-scooters when we charge them, or even electrical cars, and this fire is almost impossible to stop. And the reason there is that this is a liquid electrolyte, or a liquid which dissolves the electrolyte, and this causes finally the fire. And so the idea came up to make all solid-state batteries where this electrolyte is a solid electrolyte. Mm-hmm. And this was part of our research, that we looked for new materials, and especially to understand the process of the small lithium. This is an additional important point. It's not only light, lithium is small, so it can easily migrate from the anode to the cathode when we charge and discharge the battery. And we looked out for compounds that we also get a better understanding for this lithium migration. And this was what we did quite intensive the last 10 years. Mm-hmm.
But your research is also much broader, and you're also looking on research, but also on applications, is that?
Yes, this is something, I mean, actually we did, we investigated a long time before alloys, and this is a combination of metals, various metals, and we used also so-called alkaline metals. And they gave the alloys a very specific structure, which was fascinating, just sometimes from an aesthetic point of view when we solved those structures. And lithium is an alkali metal as well. And when it became such important that we need, that lithium batteries became so important, we couldn't just use our knowledge, which we have trained ourselves for lithium, to use it for these applications in lithium-ion batteries. Mm. But certainly we also have other topics like materials for solar cells, but it's principally always on a basic level. And with respect now to lithium-ion batteries, it's the first time we really got closer contact to electrochemistry and also to industrial or to companies to make maybe a working device of those batteries. Only a small portion of a working device. A battery is much more complicated, as I have described it, but to understand the basic principles, you anyway have to build a battery at one point, and this made it very interesting the last years to have all those various corporations also.
Mm-hmm. And what is most exciting for you in research?
I mean, if you have an idea and it works out, and the students can make it or something, it's also exciting if they come with their own ideas. I just mentioned all the new corporations you build up, and you have to learn those techniques. Not only to learn the techniques, you have to understand the techniques. Your colleagues maybe do the measurements for you. So it's always exciting to study something new. And then it's always exciting if unexpected things come up. Like when we make new alloys, I come back to this example as well, and you suddenly get a very fascinating structure. Mm-hmm. And in this context, when we made our first measurements, when we had the first compounds, and then we saw, oh wow, this is a good ion conductor, let's go on in this business. So actually the first compound was a little bit accidentally, we were working in a similar field, and then these are exciting moments.
Mm-hmm. And so structure is also important for you?
Yes, so we use lots of neutron diffractions where we have to go to large facilities like the FRM2 in Munich, or just recently I visited ENSTO in Sydney, and so this is an interesting cooperation. Mm-hmm. So we need all kind of structure determination techniques to solve the structure, and actually yes, we are very interested in understanding the physical properties on an atomic level. Mm-hmm. And for this we need exactly to know how the atoms are located relative to each other. And in this context for lithium, lithium is a very light element, as I said, and it's difficult to find it in those structures, and especially to see maybe a migration where it goes. Mm-hmm. And for this I think we synthesized really well-defined compounds, and so we are lucky to get through those measurements quite an idea what makes the lithium ion to migrate through the solids.
Hmm. And when you talked about applications, it was sounded like you're always looking at sustainable applications. So the motto of the conference we're currently attending is Rethinking Chemistry. Is that a topic which is also seen in your research? Yeah.
So, I mean, the point is, as a chemist, I think we were always rethinking. We had to rethink always the things. I mean, the topic chemistry is closely connected to chemical industry. This is quite a difference to physics. There's no physical chemistry. So I think we chemists are always facing the problems to be in discussion with people, with society, and think about the problems we create. And we had many environmental problems in the old days, which we had to rethink all the time. And currently, rethinking chemistry would, in the ideal case, certainly be, for example, in photovoltaics, if a new production process starts, that we get very early to think about how will we recycle the material. And this is not always possible. For example, in our lithium ion conductors, I think with respect to recycling, getting from a really basic result to already thinking to recycling, that's too early. Because sometimes we just need to understand the basic principles. But if you go to the application, getting upscaling of the compounds, like in the so-called, which work really good, perovskite solar cells. This is not exactly our topic, but the perovskite solar cell is a really extremely solar cell with a high efficiency, but it's based on lead. And many research groups go into this field, and it's fascinating. But those people who start to upscale it, to make devices out of it, maybe making startups, then it has to be it's very important. And at this point, I think rethinking is important, to think about if it's the right way to go, and not realize maybe in 10 years, no, now we create another problem.
So do you think that also at the university, early on, you have to think about maybe the applications, although you're on the very basic level of research?
I think not really. I think fundamental research should be kind of independent of this. If we have these thoughts, because we don't know if this would be maybe a compound or a material which will go into the application, but then we would lose lots of knowledge, I think. So to build up knowledge on fundamental research is important. And I think when we go to the production, then I mean, it's not necessarily that we should not use those compounds, but we have to think quite early how we could use those. But on a fundamental research level, I think this would be too early. This would stop our curiosity also.
And if you would say in 3 words, what makes a successful chemist, and how can a young chemist grow into that?
Okay. For me, it's always curiosity to look behind the things. So curiosity is one a big topic. Then to be consistent working, so that you stay, I don't know, I look for the English word, that you just continue in working. And the third thing is, respect for nature. I think this is something, even we make a very simple alloy, nobody thinks an alloy, but this is nature as well. It's a natural process, and this is something I think is important.
Yeah, I like that, respect for nature. I think it's not the first thing we as chemists think about.
But nature is chemistry by
Yes,
itself.
sure, it is.
And there are also research fields where we learn how nature is doing things. I mean, there's lots of things to learn. I mean, if you would be able to work like a leaf and doing photosynthesis, this would be great.
Yeah. And how do you try to educate or foster young talent?
Okay, do you mean more in a general sense or with respect to this topic?
To your in your research group.
Yeah. So there are PhD students and young researchers which start their independent academic career. So we have to, and also the students which were educated. So there are 3 levels of students. So during teaching, currently I'm also teaching the engineers in chemistry, and I found it quite interesting to pick up news headlines from the news and bring up the headline and tell what does this mean, and then we go along the headline and work down basic chemistry, just very simple principles. So this is one of the things where I hope that I can, for example, hydrogen production. This is now a big issue. We want to go into storage energy in hydrogen, and hydrogen production is done by electrolysis. And this is maybe done in other countries. Maybe so we have contracts now with Canada to do hydrogen production in Canada. And then the question is, how comes the hydrogen to Europe? How is it transported, and how do we get the hydrogen? Maybe we have a different compound. People think about ammonia, to make ammonia, because this is then can easily be liquefied, and then this comes by ship to Europe, and then we have to get the hydrogen out again. And these are all basic principles to really teach refreshment chemistry also for engineers, how ammonia production, which we use for fertilizer, is produced. So I'm trying to put like general contexts or specific contexts from the daily news into the lectures to get more interest, and also thinking about those problems. That it's not so easy what we read in the newspaper. All the problems seems to be solved, and if you think about, for this electrolysis you need catalysts, and to get hydrogen out of the compound, to get it back to hydrogen, you need platinum metals. So there are many topics which has to go out, and you can just go along this line and teach refreshment chemistry on this.
Yeah, it's fascinating.
Yeah. Then on the level of PhD students, I mean, this is maybe not exactly this general thinking, but a critical thinking. I think this is important for those, and we have something which we call a hot paper seminar. So if another group publish something which is closely or maybe not so closely related, so they should pick up such papers, or they have to look around maybe twice a year, it's not so often, and then you have to present this paper to the group like they would be a reviewer of the paper, to look at the critical aspects of the paper, to tell what is good, what is bad, maybe what is missing, and by this I hope they get a critical view just on their own research.
Great. And do you also do something to fascinate younger students for chemistry? You mean students in school? Yeah. So I like to do experimental lectures, and sometimes I do these experimental lectures for when we have a day where all the students, pupils are invited to come to school. This is something which I like to do myself, and this is in chemistry. I think it's easy really to get excitement out of the people. You can make small explosions, you can make nice colors and things like this. And yeah, when my kids were small, I even went to elementary schools and played around with very daily, not very
certainly no toxic things, and gave impression what chemistry means.
And so what fascinates you most about chemistry?
Oh, for me it's that so many unexpected things can happen, that we can create new things, that we just make something which is totally new, which was not there before. And chemistry is a science which is really broad. So I studied chemistry and mathematics and had to make a decision where I do my PhD, and chemistry is also pragmatic, and you need like experimental skills, so you do something with your hands. Even you have to clean up after the day. This is something which is quite different from a theoretical thing. But chemistry is so open. We can go in the direction of theory. We can go into the direction of applied research, physical chemistry, so close to physics. So I think chemistry is like getting from all kind of sciences an input and brings things together. It's quite complicated, and it's not as complicated as biology or molecular. This is even maybe on a larger scale. Chemistry is on a still molecular level, so it's good to control and have a good overview. So this is what makes fun for me.
And also during your career, you moved lots to a lot of different research groups and different countries. What did you take away from that?
Oh, this is one of the really good things. Certainly from a personal point of view, at one point it's important to stay at a place to build up your personal life, maybe with family or friends, and have a constant thing. But so I really moved around a lot. So one of the exciting things, go to Chicago, where I did a postdoc, and to work in a totally different research environment. I also did theory there, I started new methods there. And then I went to Switzerland. This is also a very different research environment, even it's not that far. And even in Germany, I worked at 2 or 3 universities. And to have like colleagues and friends all over the world through this is a nice side thing which comes with it.
And you're also at the Advanced Materials Science program at the elite university. Do we need elite universities in Germany?
Yeah, this is an interesting thing. First of all, I think elite or elite in Germany has maybe a different meaning than in the English word. So elite in Germany is always it's better now, but 10 years ago, or this was already 20 years ago, this was a program of the Bavarian state. This was like controversially discussed. In German we have like an expression which is called Begabtenauslese or Forderung, Begabtenforderung, which means attracting the best students. This expresses it more what it means. So I think in Germany at universities to study chemistry, which is a great thing, it's free, doesn't cost anything for the students, which I think is important. And this is almost equal at the universities. I think we don't need a separation of universities there, and we shouldn't do this. So we should keep this as it is, that the education is similar, it's good, we have a high standard here. If it goes to more advanced studies, like master thesis or PhD thesis, and it gets more research oriented, then certainly students are attracted by universities where more research activation is going on. And to have a competition on this level between the universities, I think this is okay.
And if you would have unlimited funds for research, what would you do then? Or maybe for education? I don't know what you would like to spend it.
Certainly in chemistry we need good experimental skills. And I saw in Corona that we even reduced this. And Germany has a good standing internationally because we have good experimental skills. And to give more opportunities to the students to have a really good laboratory equipment, and they can start also on an early point to do maybe some research topics. This would be good. And for teaching, certainly we have a tutor programs, and this could be increased to get a more intensive training for the students. But yeah, infinite research money, this is like, it's so crazy to think about. I think it's still good to have a competition, that you use it in a sensible meaning. I mean, I think independent research money would actually not be good. So I grew up in South Germany. We have learned to keep the money together, and this concentrates you on the thing. But certainly to have, so I have a group which does state chemistry, which does solution chemistry, physical chemistry, electrochemistry, and to bring this closer together in a unit and have to maybe a substructure with people who organize this. I think for this it would be good to have more money and maybe also good equipment and laboratories. So we looked for in other fields to gather this money, to save time, to have just money, build maybe a very good infrastructure and bring people together. This is fascinating.
So how do you encourage young researchers to start an academic career?
Yeah, so I had and I have always some young research groups at my chair, and so generally it's not, there's no need to really scientifically advise them, because they come with ideas and maybe they have already a small research grant. But I feel always happy to coach them a little bit, to give them a stable research environment, because it's also on a personal, very insecure way where they go. So to look for laboratory space. Often they come with stipendships, which have no social security. So I make this point to them, because often good students have stipendships without social security, and at the end this doesn't count out. So maybe I give them small contracts parallel to their stipendship, that they get those social securities. Yeah, and then just also involve them in teaching. I think this is good, that research is only one part of it. If they want to stay in academics, that they should also have fun in teaching, and because they only judged, or mainly judged, on their research output. And so it's quite difficult. I think it's quite a task for the young researchers. And there's also this political point. So when I was in the Wöhler Association, a member of the Wöhler Association, we created together with the BASF, the so-called Wöhler BASF Young Talent Prize, to give, to promote also young researchers and to get them a face, and this I think is as important as well.
And you in the beginning said that research topics, you also sometimes they come up because you discuss with your group. But how do you in general find research topics and then decide which ones to follow up?
Yes, I mean, when you start with topics, at my time you were looking out for something nobody else did. And for me it was always fascinating to be in the field. I did my PhD in organometallic chemistry, which is molecular chemistry, and then I continued also in solid state chemistry. And the idea is to make a chemical connection between the two fields. And currently, this took quite a while to use, for example, alloys, to dissolve them and make them in solution, to bring them into solution. And now we can use those, for example, to get highly concentrated solution of silicon, which again we use for solar cells. So there's always a basic, for me it was always to get the knowledge, basic knowledge on what nature does actually, what chemical reactions can do, and then quite often an application pops out of those results, and then I have to get in contact with colleagues, or they approach me, and to contribute with synthetic methods to the thing. And if also active PhD students, I mean, they think independent, suddenly come up with an idea, this opens also sometimes new research fields in my group.
So thank you very much for the interview.
Thank you for giving me the chance, giving my ideas here.